Hi, you're with Mr. Laurie, and this is part 10 of the linear and nonlinear relationships topic. We looked at cubics last lesson, and now we're going to be looking at further polynomials. So these are curves where the power is going above 3 to 4, 5, 6, in fact, any sort of power, and that's why we're going to generalize the power with the letter n. So before we get started on doing some notes, let's have a look at Desmos and have a play around with what happens when we increase the power. First, we'll start off with the standard y equals x squared. So there's our parabola that we're well and truly used to by now. Alright, let's introduce y equals x cubed. So once again, this is a curve that we should be familiar with now. Remembering that for the parabola x squared, it's completely above the x-axis, this blue curve here, because when we take a negative number and square it, we get a positive number. The cubic, on the other hand, everything on the positive side stays above the x-axis, but all the negative x values, when we cube those, we get a negative y value. So that's why it's down here. Alrighty, so what about if we up the power from 3 to 4? Y equals x to the 4 is a very similar type of curve to y equals x squared. If we take any positive value of x and raise it to the 4th power, we get a positive. And the same with any negative value of x. When we raise it to the 4th power, we'll get a positive. We can see that from 0 to 1, the x to the 4 curve lies underneath the x squared curve. But then once it goes through 1, it's steeper, and it will remain steeper for here on in. Okay, what about y equals x to the 5? Any thoughts on what that might look like? Alright, that's this purple line here, and we can see this is similar to our cubic graph. Y equals x to the 6. That's our black curve. Another one that looks similar to the parabola. And y equals x to the 7 in red. What do we notice so far? Hopefully you can see that when we look at the even powers, they give us curves that look like parabolas. And if we look at the odd powers, we get curves that look like cubics. Alright, let's take this information that we've looked at here and write a few notes. Curves that have an even power, like 2, 4, 6, and so on, all have a shape like a parabola. So curves with an even power will have shapes like parabolas. Now remember, our standard parabola is y equals ax squared. So that's for even powers. And what did we see with curves that had an odd power? Curves with an odd power will have shapes like cubics. And cubics, or the standard cubic, that we've looked at is y equals ax cubed. So odd powers will look like cubics. Let's sketch this briefly. We can have our positive parabolas, or we can have our negative parabolas. Okay, so if a is greater than 0, or if the coefficient a is less than 0, that's what our parabolas will look like. But this is the curve, or the general type of shape that we'll get when n is even. When we look at our cubics, the basic cubic looks like that when a is greater than 0. And if we make a less than 0, our cubic goes the other way. Well, if our power of n is odd, it will have this general shape. Let's now look at what happens when we translate or move our curves up and down. When we looked at parabolas and we adjusted the equation by adding some constant on, we saw that it moved our parabola up or down. Likewise, if we changed the sign, it flipped it upside down. Well, the same properties apply if we're looking not only at x squared, but at x to the 4. If we add a constant, it simply moves our parabola up or down. And if we change the sign, it flips our parabola looking shape, our quartic, upside down. The same happens with our cubic looking graphs. So y equals x to the 5 looks like this. If we make it a negative, it goes the other way. And if we add a constant, it moves it up or down. Adding on or subtracting some constant d causes our original graph, y equals ax to the n, to be translated or moved up or down. By d units. Let's do a few sketching examples now to finish off this lesson. In our first example, we're going to look at sketching the curve of y equals 1/2 x to the 4. Have a look at the power. Is it even or odd? Because it's an even power, this curve is going to look like a parabola. So in order to sketch this, not graph it, you don't have to be specifically accurate, just sketch it. We can draw something like that. Let's do a second example. Y equals minus 2x to the 5. Is the power even or odd? Since we're dealing with an odd power, we're going to have a graph that looks like a cubic. However, the coefficient out the front is negative. So rather than going this way, our cubic graph will go this way. Or I should say, our polynomial that looks like a cubic will go this way. And once again, because it's a sketch, that is sufficient. Alright, final example. Let's sketch the graph of y equals -1 minus 2x to the 6. It might help if we rearrange this slightly so that our x term comes first and then we have our constant term at the end. If we didn't have the -1 at the end here, what would the curve look like? Well, the power is 6, so it's even, which means it's going to look like a parabola. But the coefficient out the front is negative, so it would be an upside down parabola, like this. However, when we do take into account the -1 at the end, that means that we have to move our parabola down by one unit. So on this sketch, it's important that we label this point as -1 here. So the green curve is our sketch of y equals -1 minus 2 times x to the power of 6. Okay, that finishes our lessons on graphing polynomials. Thanks for watching.